Start our second session of our non-associative day. There are also 3 speakers in this session. The first speaker is Professor Zhao Xiangui from China. The title of the talk is Growth and the Gelfand-Kirillov Dimension of Brice algebras. Let's welcome.
Okay, thank you very much, Professor Singh. I would also like to thank the organizers, Ivan and Jova. Thank you to give us this very good opportunity to share our studies. For today, my talk is based on an ongoing joint project with Qiuhui Mo, and Zhang Wenchao. In my talk, I will be talking about 4 parts. First, I will give you an introduction to growth and the GK dimension, and then I will introduce the Brice algebras and the free Brice algebras. After that, we will discuss GK dimension of Brice algebras, and finally, I will share some questions that we are still working on. Okay, the first part. How do we compare the quantities of algebras? For example, algebra objects. For finite sets, we use the number of elements cardinality, right? For finite dimensional vector spaces, we use dimension. We can say R cube, the dimension is greater than R square as R space. For infinite dimensional spaces or algebras, what can we use? For example, how to distinguish these 2 polynomials algebras. The first one is with only 1 indeterminate, and the second one has 2 indeterminates. How to distinguish them? Here, both of them, the dimension of both of them are infinity. So we cannot use dimension to distinguish them. So in this case, we have some useful tools. For example, the growth and the GK dimension. Okay, let's see some definitions. Let F be a field. To be safe, we suppose the characteristic of F is 0. And a finitely generated F algebra. It would be associative or Lie algebra or Jordan algebra, and so on. Which is generated by a set X, a finite set. This set is called generating set. AXN, here AXN, this one is the subspace spanned by all monomials in X of length less than or equal to n. And we use fxn to denote the dimension of AXN as a vector space. So we can see that this function in n is increasing, and it depends on the set X. And this function measures how fast the algebra is growing with respect to X. So it's a very good function, but the bad news is that this function depends on X. So we want to remove the independence. In order to do that, we introduce some equivalence relation. So now let's phi be the eventually monotone increasing function from natural numbers to positive reals. To such function f and g, we say f is less than or equal to g if there exists some natural numbers, positive natural numbers, c, m, and n, such that f of n is less than or equal to c times g of mn. for all n greater than capital N. And we set f equivalent to g if f under this relation, f is less than or equal to g, and g is also less than or equal to f. It's a lot difficult to check that. This relation is an equivalence relation on the set phi. So right now we can talk about the equivalence class. For any function f in phi, this equivalent class is called the growth of the function f. Now return to the algebra. If x and y are two generating set of A, then they have the same growth. This fact is not difficult to prove. So right now we can define the growth of algebra A just as the growth of the function with respect to any generating set. Okay. How to erase the remark? Okay, now a finitely generated algebra A is said to have polynomial growth if the growth of A is equal to the growth of some polynomial n to the d. Exponential growth if the growth of A is the same as the growth of this exponential function e to the power n. And intermediate growth if the growth of A is less than the exponential growth, but not less than any polynomial growth. Okay, alternative growth. In this talk, we don't need this notion, so we just skip this. Functions within right range can be realized as growth functions of finitely generated algebra. Recently, Bell and Zamenhof give a complete characterization of the functions that can occur as the growth function of finitely generated associative algebras. But the bad news is that the growth of an algebra is often quite hard. Now we turn to another notion, Gelfand-Kirillov dimension. This notion is a numerical characteristic of growth, and often it's not so difficult to compute. So now we can define the GK dimension. The GK dimension of a finitely generated algebra A is defined as the limit soup of the log sub n of this function. This function fx, recall that this function, where x is a generating set of A. So let me go back. So what is fx here? Fx is the dimension of axn, and axn is the subspace spanned by all monomials in X of length less than or equal to n. Okay, this is a definition for algebra, a finitely generated algebra. For general algebra, we can define the GK dimension of A as the supremum of the GK dimension of finitely generated subalgebras, like this. So this notion is defined for any algebra. And here we note that the GK dimension is a closer notion than the growth. That means if two algebras have the same growth, then they have the same GK dimension, but the other way around is false. So here's some history background. Growth and GK dimension was introduced by Gelfand and Kirillov for algebras, also by John Miller for groups. And now the GK dimension becomes a standard invariant for the study of algebras. Let me show you some examples. First, if the algebra A is associative and finite dimensional, then the GK dimension is 0. And if A is a polynomial algebra, where here the GK dimension is just the number of indeterminates. For example, the GK dimension of Rx is 1, and the GK dimension of Rx1, x2 is 2. So we can answer the question on the first page, maybe the second page. We can use GK dimension to distinguish those two algebras. For free associative algebra, even in two generators, the GK dimension is quite large. It's infinity. And it's known that the range of the GK dimension of associative algebra is like this. It could be 0, could be 1, or could be any real number greater than or equal to 2, and also could be infinity. So we write in this way, the range of GK dimension of associative algebra. From here, we can say there are two gaps. The first one is open interval from 0 to 1. This gap is quite easy to prove. The second gap is the open interval from 1 to 2. So this gap, the existence of this gap is Bergman's gap theorem. Let me give you some characterizations of associative algebra of low GK dimension. If the here A is a finitely generated associative algebra, then GK dimension is 0 if and only if A is finite dimensional. So in this sense, the GK dimension measures how far an algebra is from being finite dimensional. If it's 0, then it's finite dimensional. Okay, so GK dimension 1 implies the algebra A satisfies a polynomial identity. And what about GK dimension 2? So this one is not easy. It's related to the classification of non-commutative projective curves. Now part 2. Let me give you the definition of brace algebra. A brace algebra, BA for short, is a couple A and some operations, where A is a vector space, and this angle bracket is a family of n-array operators defined for all n greater than or equal to 2. So here, these operators take an tensor up to A1 to just this element. It's with angle brackets. So here, A1 is kind of the special one. And this operation satisfies some compatibility condition. Here, if the special one, the special argument A1 is again some brackets, then we have this relation. So it's a sum of some brackets. Let's look at this bracket. So here C. So here C is the same C, the special one, right? The special argument. Then B1, B2, and Bn. Here, what is V1, V2, up to V2n? So here, this sum runs over the partitions of the ordered set AI into consecutive intervals. So here, the consecutive intervals of those AI. Let me give you some example. If M is 1, N is 2, that means we want partition this set A1 into 3 consecutive intervals, right? So we have several ways. So the first one is we can put A1 at the beginning, and then we can put A1 in the middle and at the last. So you can say we have 3 ways. So if we have M is 2, that means we want to partition A1, A2 into 3 consecutive intervals. We can do this like, so we put both elements at the beginning, and the other 2 places are empty sets. And we can put one element at the beginning, one in the middle, and so on. So we have many ways to partition this set. So here, the compatibility condition says that for any such partition, we can form a bigger bracket like this. So here, C is the same special one C, right? C is the same C, and here V0, and V1 and B1 here is a smaller bracket. So if V1 has only one element, then this is a binary operator. If V1 has 2 elements, then this is a 3-level operator. And if V1 is the empty set, this part is just B1, just B1. Okay. I just copy the compatibility condition here, the equation 1. Let me give you some concrete examples. Let A be an associative algebra, so we can define n-array operators on the vector space A as follows. So we put n elements here, and we define this to be the product B1, B2, B1 if n is 2. That means if we have only 2 elements, we just multiply them together. If n is greater than or equal to 3, then it's just 0. Just 0. So there are only 3 partitions of the single element set into 3 consecutive intervals. We just saw this. So now we want to verify the compatibility conditions here in 1. So that means we need to verify this bracket CBA, this one. We want to verify that this one equals the sum of 3 brackets like this. So we simplify this. So here is just the CBA, and the second term is just the CB together, and then A in the special place, and the last one is like this. But in by definition, the here this term is just 0, because here this term n is 3, and we know if n is greater than or equal to 3, then the n-ary operator is just 0. So the first term in this sum, the first term and the last term are both 0. So finally we got only one term. Okay. We continue this example. So we need to verify this compatibility condition. That means we need to verify C times BA equals CB times A. This is true because now we are in associative algebra. This is just the associativity. As a result, we can say that this A with this brackets, a family of brackets, is brace algebra. On the other way around, on the other hand, if we have some brace algebra A with trivial n-ary brace operators for all n greater than or equal to 3, then it's easy to check that this is if we only consider the binary operators, the binary operator, then this is an associative algebra. So that means the class of associative algebras is just the same as the class of brace algebras with trivial n-ary brace operators for n greater than or equal to 3. Another example, if A is a brace algebra and we consider the binary operator, then the compatibility condition gives us this identity. So now if we put x circle y equals just this binary brace operator, then we get a Qiuhui algebra. So it's also known as Novikov algebra. Today in previous talks, Dr. Zhang Zherui, and Professor Bai Chengmin also mentioned this algebra, Qiuhui algebras. So from this example, you can see that each brace algebra has a Qiuhui structure. Even more, if the brace algebra is free, then as Qiuhui algebra is also free. So here some history background. Brace algebra was introduced by several authors in the 90s, around the 90s in the last century. And from the literature, we can see that brace algebras have close connections to many other important classes of algebras. For example, associative algebras, Qiuhui algebras, and some bi-algebras, dendriform algebras, and so on. Here's some recent results. Here I want to mention, okay, the second one. We just mentioned that the free brace algebra is a free Qiuhui algebra, and that is also a free D algebra. We can also introduce the Gorbachev basis theory for brace algebras, and we can prove some kind of PBW type theorem for universal enveloping brace algebras of Qiuhui algebras. Now let's introduce the free brace algebra. Let X be a set of letters. Each X is called a brace word, BW for short, of degree 1. If UI is a brace word, of degree ki, then this bracket is called a brace word of degree k1 plus k2 plus kn. So here each ui is a brace word. So that means a brace word is constructed from brace words. Omega x be the set of all brace words on X. And the brace word is called or normal brace word if either this word is a letter or this word is this kind of bracket with the special place a letter from X. And we use n of X to denote the set of all normal brace words on X. For example, here if X is the set X and Y, we let A, B, C, D be from X. For degree 1 word, brace word, we have this type A. A could be X or Y. So the blue ones are normal brace word. For degree 2, only one type. For degree 3, we have several types. For example, here we put a C, a single letter here, and AB like this. So it's the arity is 3. We can also put A, B together in a bracket. So here AB is A and B are the input of the binary operator, and then as a whole, it's the first argument of the binary operator. For degree 4, we have much more like this, right? Okay. So if we only look at the word, it's kind of complicated. The good news is that we can relate the normal brace word and the labeled planar rooted tree. So they have a one-to-one correspondence. For letter A, we can use the tree, labeled tree, labeled by A. Here the tree has only one vertices, low edge. BA, we can use a tree with 2 vertices, labeled by A and B. A is at the bottom, so we call here A is the special letter A. Here is corresponding to the root of the tree. So similarly, we can write this brace word, the third one, as a tree which has 3 branches, right? And the more complicated one as a more complicated tree like this. So from A we have 3 parts. So here the first B, the right one is B. The middle one is again, it's a bracket. So it's in brackets. So it's kind of subtree. So the left one is F like this. It's lower than that. It was shown by Captain that the normal brace word forms a linear basis of the free brace algebra generated by X. So if we here, so it's a linear basis. The operators on the normal brace word is like this. So for any normal brace words, Vi and W is like this. So the product, so here's W in the special place, but W is also in brackets. So by the compatibility condition, this one is a sum of some bigger brackets. So this sum runs over partitions of the ordered set Vm down to V2, V1 into consecutive intervals. Here we have 2n plus 1 intervals. We can also understand this by the labeled planar rooted tree. For example, okay, I just copy this condition. So this can be printed by trees. So the easy one here, here I didn't write the Vm as a tree. We can also do that. It's just one vertex, right? One vertex. So this brace brackets is equal to the sum of the bigger trees. So let's look at the bigger trees. They have the same root x, and V0 is here. So V0 is grafted to x, and V1 is grafted to U1. V2 is grafted to x, the root, and V3 to U2, and so on, and so on. Okay. Now let's consider the GK dimension of brace algebras. Here, the main theorem is like this. For each real number r greater than or equal to 1, there exists a two-generated brace algebra with GK dimension r. So as a corollary, we can say that Bergman's gap means the gap between 1 and 2. So Bergman's gap theorem for GK dimension does not hold for brace algebras. Recall that here we want to show that for any r greater than or equal to 1, we have some brace algebra with GK dimension r. We already know that for each real number r greater than or equal to 2, there exists a two-generated associative algebra with GK dimension r. And we know that any associative algebra can be viewed as a brace algebra, or we can define a brace algebra from associative algebra. So that means for n greater than or equal to 2, it's clear. So in order to prove this theorem, it suffices to prove the case for r just between 1 and 2, right? So we just want to show this gap does not exist. Our goal is to construct a two-generated brace algebra with GK dimension r, some fixed r, in the open interval from 1 to 2. Here we let x be the set of two letters, x and y. We use this notation, gn to kn. This part means here we have kn copies of gn. Here g1 to the power k1 means we have k1 copies of g1. So here we have only, you can say we have it's kind of we have only one pair of brackets. So here each ki is a natural number, would be 0, and f gi from the free Brice algebra. They would be a monomial or a polynomial. And by definition, we just denote f by this. So if the those ki are 0, then it is just f. Now we let theta be r minus 1. Recall that r is from 1 to 2, is between 1 and 2. So theta is between 0 and 1. So n theta is a number, depends on theta. It's a minimum natural number such that n minus 2 minus n to the theta is positive. Because theta is less than 1, so such n exists. So n theta is well defined. So now we define a set W sub n, which is a set of some normal Brice word like this. So here's in the special place we have y, and before y we have some number of x, and then y, and then some number of x. So here we have two y's. We have two y's, and n minus 2x. That means a plus b is n minus 2. And here we put some restriction on b. b is greater than 0, greater than or equal to 0, and less than or equal to this number. This number, okay. And then we put those Wn together, we get the set W. So W consists of normal Brice words such that those words has two y's and satisfy this condition. So now we denote the complement of W by C. Here that means C is all the words with two y's, set minus the set W. So okay, remember that any word in C has two y's, and one y is just at the special place. So now our idea is like this. We want to construct a set S of normal Brice word such that the quotient algebra, okay, the quotient of the free Brice algebra generated by X by the idea generated by S. We want this algebra to have a linear basis B. B has okay, B is the union of the set X, and the second part is like this. Here, special place we have Y, and the other places are all X. If I is 0, here if I is 0, we just get Y. So both X and Y are in B. And also C. So here B is the union of three parts. The first part, in the first part, there's the Y. In the second part, there is just one Y. In the third part, C, we have mentioned that C, any word from C has two Y's. Okay. We write Cn, C sub n, the subset of C, and the element in Cn is just the element in C whose degree is n, the degree n part. We define this one is because we know what C is, so we can just write down Cn. if n is small, there has low restriction. We just have this kind of words. If n is big, greater than or equal to n theta, then we have restriction on B. Here, restriction on B. But A plus B equals n minus 2. So we can translate this condition to some restriction on A. We can write like this. A is greater than 0 and greater than or equal to 0, less than n to the power theta. Now we count the number of words in Cn. If n is small, it's just n minus 1. If n is greater than or equal to n theta, it's just the C of n to the power theta, where this notation means the minimum natural number such that m is greater than n to the theta. As growth function, this one is just the equivalent to n to the power theta. So if we compute the dimension of AXN, recall that this means the subspace spanned by monomials of length less than or equal to n, right? So here we want B. We want the set B be generating set. So with the length less than or equal to n, that means we add those cardinality C1, C2 up to Cn together, because Cn is when n is big, this is equivalent to the power n to the theta. So when we add them together, we get the sum is equivalent to n to the power 1 plus theta. So as a result, the GK dimension of A, the quotient algebra A, is just 1 plus theta, that is R, as desired. So now the only problem is that we need to check. We do have some brace algebra with linear basis B, right? So we do this. So we do this by a technique of Gerber-Schultz basis. So here the tricky part is constructing the set S. So how to do that? As before, X be the set, X and Y, and we use this notation to denote a degree Y, the Y degree of the word W, and the height. Okay, the height of W is defined by if W is a letter, then the height is 0. So let me go back. So the height is just like, you can say here, if we look at the tree, a letter A, so the height of this A is 0. So the height of this brackets BA, the height is 1. For the third word, the height is also 1. For the last, the height is 2. So this is the idea. Okay. So if the word is a letter, then the height is 0. If the normal word is something like this, so here Z is X or Y, HUI is a normal brace word, then the height of W is just 1 plus the maximum of the height of those UI. Okay. Then we use phi 1 to take the value of A here. For each word in W, phi 1 of W, phi 1 of that word is just A. That means the number of X before the first Y. And the phi 2 for the number B. And then we construct another set, W tilde. So here we this is a subset of W. We eliminate some word from W to get W tilde. How to do that? So in W tilde, each word U in W tilde satisfies the condition. For any other word V in W, if U and V have the same number B, if they have the same B, then U must have less A than V, or at least, or at most has the same number A as the same number A of U as V, right? Like this. So, for example, if U is a word like this and V is like this, U and V have the same B, 3. And for U, the A is 2. For V, the A is 1. So here, because here 1 is less than 2, and so U is not in W tilde. So the bigger A will not be in W tilde. So now we can define several sets. The first S1. S1 means the words, normal words of height greater than or equal to 2. And set S2 means the normal brace words of Y degree greater than or equal to 3. And S3 means brackets like this. So in the special place here, we have X, not Y. So, okay. And the S4 is here in the special place, we have U from W tilde. And before U, we have some X. There's no Y. And we put those SI together, we get S. Then we can prove that this S equals, so this S is we don't need this equal sign. S is a Gorbachev basis in the free brace algebra. Here the notion of Gorbachev basis, we didn't introduce this notion in my talk because I don't have enough time. And by the composition diamond lemma, so which says if we have a subset from the free brace algebra satisfy some Meyer conditions, then the following 3 statements are equivalent. So here we need the equivalence between the first and the third one. The first one, S is a Gorbachev basis. So we have checked that in the previous lemma. The third one, the irreducible set, this set, okay, whatever, it's a set of normal brace words, is a linear basis of the quotient algebra. So we have checked, we have seen that the S we constructed is a Gorbachev basis. So by the composition diamond lemma, the irreducible set is a linear basis. And we can check that this irreducible set is exactly the set B we used before. So our theorem is proved. Okay, the final part. Here I share two questions with you. We are still working on those two questions. So question one, calculate the Brice algebras of GK dimension 0. So recall that for an associative algebra, GK dimension 0 is GK dimension A is 0. If and only if A is locally finite dimensional. That means every finitely generated subalgebra of A is finite dimensional. Okay. This condition, denoted by star, actually many other classes of algebras has this equivalence. Star, okay, like associative algebra, right? We just mentioned this. For Lie algebra, it's also true. And for associative superalgebra or Lie superalgebra, quadratic Jordan systems. But we also know that for some classes, the star does not hold. For example, for the classes of non-associative algebra. Actually, we have some example of non-associative algebra, which has GK dimension 0 and which is not finite dimensional. Star does not hold for quadratic Jordan superalgebras, nor for Jordan special superalgebras. So it's quite natural to ask, does star hold for our Brice algebras? So this is our first question. Our second question, what is the range of GK dimension of Brice algebras? Recall that for associative algebra, the range of GK dimension is just the set of 0, 1, and the closed interval from 2 to infinity. So here we have two gaps. For Lie algebra, there is only one gap. The open interval from 0 to 1. And for the general non-associative algebra, there is no gap. That means any non-negative real numbers and the infinity could be the GK dimension of some non-associative algebras. And we also know that for non-symmetrical operators, the range of GK dimension is the same as associative algebras. There are two gaps. So for Brice algebra, we already know that for any r equal to 0 or greater than or equal to 1, even infinity, occurs as the GK dimension of a Brice algebra. But we don't know, right now we don't know whether there is a gap for the GK dimension of Brice algebra from 0 to 1. We don't know whether this gap exists. We are still working on this. I don't know, maybe this question is trivial, but right now I don't say the answer. Okay. So that's all for my talk. Thank you very much.
Thank you. Thank you very much. Are there any questions or comments? So I have one question. So in the definition of the Brice algebra, so there is an array operation. So are there any connection between Brice algebra and N-Leibniz algebra? Or only?
Oh, it's a good question. I don't have any answer. I have no clue for this question. Maybe some audience have some clue. Anyway, I don't know.
Okay, so also about the second question, so about the range of GK dimension. So could you move to that page?
Okay, this page. Yeah.
Yeah. So for the second item and the third item, I'm confused because the algebra is a non-associative algebra. So why are there any conflicts?
Here, for example, for Lie algebra, that means for number between strictly between 0 and 1,
Yeah.
that number cannot be the GK dimension of a Lie algebra.
Yeah.
But that number could be the GK dimension of some other non-associative algebra.
Oh, some other non-associative algebra.
Yeah.
Okay.
Yes. Yeah.
Okay. Okay. Thank you. So, are there any other questions?
Yes,
please.
I also have a question. You constructed the brace algebras with the arbitrary Gelfand-Kirillov dimension. It's maybe not a question, but a comment. It would be interesting to construct such algebras with some structural restrictions. For example, prime or simple or whatever. Similarly to problems we had in associative and other algebras.
Yes. Good point. Thank you.
Okay, so if no other questions, let's thank the speaker again. Thank you very much for your nice talk.
Thank you.
Okay. So I think we can continue